Welcome back, and yeah, we have intense discussion in the morning session, and I hope you enjoyed the second session, which will be provided by Professor Justin Song from Singapore. Right, so
Thanks very much to the organizers. Thanks, Fong, for the very kind invitation. To come here. It's the first time in Daejeon, and it's very, very nice. Had a bakery this morning. It's quite good, even though there's a very long line. So I'm going to be talking a little bit about quantum geometry, and I'm going to try to convince you guys that it has something to do. It can play a role in non-reciprocal things. I'm going to assume you guys are all experts in quantum geometry already, given the intense, discussion this morning. For any extra details, I refer you to this talk this morning by Ozawa Sensei. Also, I'm looking at the program here from last week, and I'm looking. Look at this. On Monday, May 27th, there was Katie Law talking about quantum geometry, metric and mono materials. And look also on Tuesday, Raquel. Zeros talk about quantum geometry and linear response, optical transitions, and that kind of stuff, And and actually, lots of people like Roderick talked about where the current was going through in Chern insulators. Lots of people here were talking about quantum geometry. So I'm going to take this as license to be as fast and loose with concepts as possible. And for all formal definitions, I will refer you to their reports. Thank you very much. All right. So with that, I'll tell you a little bit about what we're thinking about, and in particular, I'm going to tell you about something called non-reciprocal quantum matter. This work was done with lots of different people, mainly with the students and postdocs some who have already kind of moved on. Also with longtime collaborators, Giovanni Vignale and Mark Renner at the University. So I use this kind of long word, non-reciprocal. And I'm also not going to give you a formal definition of what non-reciprocal is. I'm going to give you a definition via examples. So when we think about non-reciprocity, we often think about this kind of paradigmic example in optical isolator, right? So what we have basically is you come in with some input. All right, so here we have some input H1. And only P2 comes out, right? So it has this kind of isolation thing. We say that this is an example of an optical kind of a non-reciprocal device, optical isolator. And there are quite a few classical examples of this kind of non-reciprocal kind of action. So I'm not going to give you a formal definition. I'm just giving you examples, right? So one classical example is that of the Faraday rotator. So I take a Faraday crystal with magnetic field, and what this allows me to do is that because of the Faraday effect, it will basically rotate polarization in a particular way, right? So it will rotate the polarization, and then if you're clever enough, put some of these polarizers on either side, you kind of twist them so they're 45 degrees, and you kind of choose the correct thickness, you can create an isolator. So this is a classic example. This kind of linear response requires broken time reversal symmetry, right? There's another example of non-reciprocity. This comes from the classic example of p-n junctions. I create a p-n diode, take p-n junction of silicon, for instance, and what I find basically is that the forward and the backward are differentiated, right? So forward biases versus backward bias gives me a different current. So, from this, I get this kind of general notion, not a true definition per se, that non-reciprocity is a means of differentiating forward versus backwards, some kind of differentiation. This could either be in a linear way or non-linear way, but, this is the kind of, rough feeling you get about what a non-reciprocal device or material is, right? Some require broken time reversal symmetry, some require, this is okay without broken time reversal, this requires just broken divergence, but you have to go to a non-linear. Okay, so far so good, happy? Great, no first questions? Very good, thank you very much. Good, and so I'd like to kind of ask, are there quantum means of achieving non-reciprocity, right? Of course, here these are classical means, right? So this comes from the Faraday effect that was found in 1800s, right? And this was a p-n junction silicon diodes, maybe germanium diode was the first one that saw it, right? So all classical things, right? So are there quantum, in big inverted commas, ways of achieving non-reciprocity. And I'll try to kind of convince you, I'm going to argue that the answer is yes, right? And I'm going to argue by giving examples. And the kind of key ingredient, key resource that I'm going to be using is geometry, quantum geometry. As we already said, we're all experts here, so I'm not really going to explain about. I'll give kind of some obligatory remarks about it. And the obligatory remark about this is that, from this parameter that we saw this morning from Ozawa saying, here we use K instead. So our kind of quasi-momentum in our block crystals, a single particle system, right? In a crystalline system, as K changes, if I'm in a kind of multi-band system, multi-orbitals, the wave functions can wind, and this winding, can describe some kind of geometry in a local sense or a topology in a global sense. So, right, and this gives rise, from the topology gives rise to a lot of very interesting things. For example, states, while some other kind of fermions, very nice things, and that's that. Right, so you see, we all understand that. One, of course, we can do this in a very formal way, but here's a more heuristic way of understanding this. Right, so one way to kind of think a little more about this is to just think about single wave packets. So let's try to construct the wave packet in free space. So I can construct the wave packet in free space by some superposition of plane waves, right? Some say Gaussian superposition of wave packets, and I can create some simple kind of wave packet, and it's centered around some position that's called the position zero, and this requires some particular superposition that I can change, that I can dictate myself, right? And if I take those same superpositions, but instead now put it into a block kind of crystal, a crystal with wave functions, which are block waves. So the wave functions that are block waves are not just plane waves, right? There's a plane wave part. There's also, as you reminded here, there's also this, periodic block part, right? Because I'm in a crystal, I'm not in a free space system. But if I do that, you kind of you will say that I would have to kind of take into consideration, this multi-orbital structure, the structure of that block wave packet, and that should somehow change, qualitatively change what I see here, right? Is it going to be this simple Gaussian wave packet anymore? So if we concentrate just on the center of mass, or the center of this wave packet, it turns out that it gets shifted, right? And that shift is given by, so if I use the same weights that I did for the free space thing, it gets shifted by the barrier connection, right? And so lots of people like to call it, I think, I don't know who was the first to kind of, popularize, I guess Blount was the first to popularize, they call it an intracell coordinate. Nagaosa likes to use this word a lot as well. And so it gets shifted by a little bit. And this has tremendous consequences, right? This tells you that just depending on where I put this, I put this wave packet, its center gets shifted around. It's shifted around by the barrier connection. And so now if I say I apply an electric field, and I can now I change, what does an electric field do? Electric fields will accelerate, right? It's a force, it accelerates my momentum, and so my case will change. If my case will change now, that means the center will change. So this will give you a velocity. So this is kind of the origin of the anomalous velocity in these crystals, right? So by just tracking the center of these wave packets and applying some force that pushes around your momentum. Yes.
Yeah, question. Could you go back to the previous slides? I'm not quite understanding of this shifting, because so this is barrier connection, right?
Yeah.
Barrier connection depends on gauge.
Yeah. This is the gauge dependent choice, not gauge invariant.
Yeah. But the wave package, I think it's we can see it, right? So it's if I have
so we make a gauge choice.
Fancy equipment, I can measure it. So it should be measurable. So the shifting of this wave package is a measurable quantity, but it relies on some gauge dependent quantity.
Yeah, so yeah, that's right. So that's great. So the barrier connection is gauge dependent. It's not gauge invariant.
Yeah.
But after you apply some electric field and it shifts around, oh yeah, by golly, this is now the Berry curvature. And is the Berry curvature a gauge independent or gauge dependent quantity?
Independent.
Independent, yes. That's it. Yeah, so you're right. I want to have gauge invariant quantities, and that's that. Of course, this picture I drew because it's just nice to draw,
Okay.
right? It's not gauge invariant, but it's just a picture just there. So far, more questions?
So I'm confused by this previous slide. So what are you plotting on the center?
Oh, so what I'm doing is I'm saying, okay, fine, if I know some particular gauge choice for my block wave functions, all right? And there's some very connection associated with that kind of thing. Let's take the same weights that I used to create this Gaussian wave packet in free space. That had EIK.R, right? That's a plane wave. But now I take those same weights and I put it in a system which not only has an EIK.R but now has a block part, right? That block part, just put it inside, keep the same weights. Let's say I close my eyes, keep the same weights.
Okay, you're not looking at like time evolution or
No, it's static.
Okay, I understand.
Okay, good, happy.
Sorry, there should a question. Here, you assume that the width of this packet remains the same.
Sorry?
Width, size. of the
Yes.
packet.
Yeah, yeah. So I made a big assumption there, but then I'm gonna change that in a second. Yes. So I try to do step by step. And so of course, because I'm doing step by step, I'm taking a lot of liberty with keeping and retaining terms because for pedagogical reasons. So yes, of course things can change, of course, as you astutely noted. But we'll see this in a couple of slides. Thank you very much. More questions, please. Very good. Happy. So we see basically that the geometry of these states and in our bands can change the kind of evolution of the wave packet. It's kind of nice. It's kind of a simple semi-classical equation motion. This is something that you would see this part here in free space, but this is like an addition, right? So this kind of Kaplan-Luttinger kind of very nice thing that you get. And of course, this can account for a whole range of things, right? So for instance, you can account for quantized non-Hall effect or even orbital kind of ferromagnetism in recent kind of twisted violet within the HBN type of example. So that's kind of nice. So, and there's a whole zoo of people trying to relate geometry to responses, right? So if you're very interested in how you want to relate quantum geometry to responses, please talk to me. Last week, they've told you all sorts of things. So they told you to think about distributive weight, told you to think about optical response at both linear order, but also at non-linear order. People like to call things that arise from quantum geometry as well. And they even say, for instance, the certain injection current and the linear injection current depend on some type of quantum metric, big inverted commas. That's why there's a big star here. Should be, but there's some idea of basically how geometry can constrain the type of responses that you get. So if you're interested, I'm very interested in this kind of stuff, but it requires, there's a whole talk on itself. So I will gloss through this, and if you're interested, come. Okay. So where I'm interested, so in this talk, I'd like to discuss a lot of different things. I'm going to give you, I'm trying to educate via examples. I'm not going to give you good definitions or anything, so I'll give you examples. I'm going to ask simple questions. Can use this quantum geometry affect collective modes? And the collective mode that I like the most is plasmons. And it turns out you can. It turns out actually, I won't tell you how for this particular case, but on the edge of a 2D metal, which has some kind of very curvature, very flux in the system, it turns out that the edge plasmonic modes, all right, can acquire non-reciprocity. And non-reciprocity being forward, remember we said non-reciprocity was the difference between forward and backward. So the forward and backwards have different dispersion relations, and it's actually given here in this case by the very flux, this integrated very curvature through the Fermi surface of the system of the metal. So this gives you some kind, we call this Carberry plasmons.
That's a question.
Very good.
Yeah. So at zero, so we know that that's 2D plasma, right?
So 2D inside here.
Yeah, 2D or surface plasma.
This is the edge of the 2D.
Edge of 2D. Yeah.
So this is a 1D.
Oh, it's 1D. Yes. But let me if it's 2D, so we know it's the plasma frequency is square root of Q, right?
That's right.
But we know that in the long wavelength limit, the speed of any collective mode cannot over speed of light, right? So in the long wavelength limit, we have to go back to linear.
Yeah.
It cannot be square root Q all the way to Q equals 0, right? So my question is here, you apply a magnetic field. So now you
It's not
see
magnetic field. This is just a
all B equal to 0. Yeah. Anyway, so the left side and the right side, they are not symmetric.
Yeah.
Right. But if I really look at the long wavelength limit, it go back to linear.
Yeah,
So
yeah.
the velocity, my question is the velocity also show some asymmetric?
So the answer is it should, but
Yeah.
we didn't calculate that, so I don't know.
Yeah.
So what you're talking about, technically speaking, comes from retardation effects. So this, you think that plasmons from a kind of technical perspective in what they call the non-retarded limit, right? So if you want to get to the retarded limit whereby they actually become polaritons,
Right.
then the retardation effect will go there, and I fully expect that they will change velocity. But I didn't calculate.
Velocity, that would be like very interesting consequence.
Yeah.
Yes. You can measure it.
Yes, very good.
Sorry, the question here that I understand that this band structure is asymmetric.
Yeah.
But if you calculate
Not really that much. This is the plasmon dispersion.
plasmon, yes, that dispersion relation. If you calculate for example, the current, then not only this the velocity, but also some density of stage that contribute. So if you use the two quantities, then probably the both directions are the same. For example, multi-channel structure, the multi-bands have the different velocities, but we only count the channel numbers, not their velocities.
Yeah. So good, fantastic, right? So it turns out when you come down to the details of the exact dispersion relations, right? It's not just counting the density states. You might think, oh, plasmons only care about density states. This is the thing that I'm trying to disabuse you of, right? It doesn't just care about density states, right? It doesn't just care about due to weight, right? It actually cares about more things, right? So I'm trying to advance that point. I'm giving you a quick example that explains anything, but it's more than that, and you'll see it a bit more clearly in future slides. This is just an introductory slides still, okay? But yeah, more questions though. Right. Yes.
So is this related to Berry curvatures or?
Yes. Berry flux
Berry flux. What's Berry flux?
is the integral of Berry curvature across the Fermi surface.
Okay, and that enters in like.
Hall connectivity. It gives you a Hall connectivity. Hall connectivity gives you some kind of impinging current into the edges, right? So if I basically go one direction versus the other direction, the impinging current in the edges is going to be different because the Hall connectivity is going to be it has a particular non-reciprocity to this, and therefore if I look at, for example, Gauss law, the buildup of charge density on the edges are going to be different as well from one direction to the other. And this is actually the main primary source of the non-reciprocity. Very good. All right, and so this is just a kind of slide that says that they've sort of seen this non-reciprocity for plasmons and zero magnetic field experimentally. So there's something here. We can talk more about this in detail, but I was going to spend more time on this, but given the questions, we'll just dissect it. Okay, good. But as you astutely pointed out, other things can change as well, not just the center of mass, right? In particular, the width can change as well, right? As we learned this morning. Right, and here, of course, I'm not integrating across the entire band. I'm just looking at a single wave packet of kind of close by to some particular people. Right. So in fact, actually, the wave packet itself can be contorted because of the quantum metric that we learned from this morning. Right, for DCLC this morning, so there's some intrinsic shape of the wave packet is determined by this quantum metric, and you can ask the question, where will we see this? Where we'll see this intrinsic shape of this wave packet? And so you say, okay, if I look at all these semi-classical things, we only actually cared about this Berry curvature stuff, right? Which is related to the Berry connection. We didn't really care about the quantum metric at all. Why? Well, it turns out that there's a very simple reason, right? So if I apply just a homogeneous electric field, a single electric field, right? This tends to basically couple with the center of mass of the wave packet. And it doesn't care whether my wave packet is large or small. Doesn't care, right? And so it directly couples with the center of the wave packet, so it's insensitive to this, size and shape of it, right? So when can I feel any contribution to the shape of the wave packet? Well, if I have inhomogeneous fields, if my electric fields are inhomogeneous, they change as a function of x, right? And then actually it turns out that the energy of electrons in this wave packet, the wave packet, will be sensitive to the size and shape of this wave packet. And that's what I'm going to try to convince you of. So in particular, we'll say that in inhomogeneous electric fields, we're going to get some corrections, right? And this will basically change the collectiveness. We're better to look at the difference between homogeneous electric fields and inhomogeneous electric fields. We're better than plasmons, because plasmons actually are just oscillating EM waves, right? And oscillating EM waves. And typically, when we look at some long wavelength limit with optical fields, with lights, we always take some long wavelength limit. We always say that the free space wavelength is much larger than say my electronic wavelength. And so then I don't really care about any variation of my electric field.
So to see this, do you need the wavelength of electric field small compared to the unit cell?
So the idea is maybe yes, but it's always going to be there. The question is how you want to enhance the effect. So it turns out that in plasmons and nanophotonics, actually you can compress the size of the EM, you can make it very, very small. In fact, actually you can actually make the wavelength of the plasma much smaller than the free space wavelength of light, much smaller. There are experiments that basically show that the full volume of the optical footprint of your light can be compressed by 1 billion times. And so by using nanophotonics in 2D and these 2D plasmonics, the hope would be that you could basically bring down these variations of these electric fields to become quite small indeed, and basically enhance the kind of things that are sensitive to the width of the wavelength, right? And so this is question here: can the quantum metric change plasma dynamics, right? And this is this first part, this second part. And so I'm just going to jump right into it and basically say that what happens is that, as we saw from before, the energy of the electrons in inhomogeneous electric field actually changes, and it's sensitive to spatial extent of the wave packet, right? And one can do a little bit of a long derivation. It's not really due to me, but due to other people, that shows that actually it's the quadrupole moment that actually gets changed. So basically, the spatial extent of the wave packet actually couples with the electric quadrupole moment, and this is actually going to give rise to some energy cost. It's going to be an energy cost of the electron wave packet that's going to be sensitive to the electric quadrupole moment of my.
So Justin, could you also provide the reference of this equation?
Yeah. Send me an email. I think.
Okay.
I'm not sure if it's here.
It's here.
Yeah, it's not. This is my paper. But
Okay.
the thing is, it's derived not in the nicest way, but okay.
Okay, yeah, just send me. Okay, thank you.
And then I'll let you deal with all the issues yourself, right? So it's your fault. But the key idea here is that this vanishes when my electric field is it's homogeneous. Right? So I need an inhomogeneous electric field. This gives some kind of energy, right? And that extra energy, so as we know, group velocity is d epsilon d momentum, right? And so I take a d by dk of this, and this gives me some extra velocity that comes from. So this is a kind of what we call a quantum metric velocity, right? And it couples with the electric control. Yes.
I mean, up to now, I mean, my knowledge that this semi-classical is related to single band. I mean, right?
Yeah.
So this quantum metric, as I learned from the philosopher, it was a multi-band physics.
Oh, it's projection onto a single band. So all the semi-classical stuff is single band, yes, but you want to project the effect of all those other bands onto that single band. Okay. That's where the Berry curvature comes from, right? Can you get a Berry curvature for a single band?
Yeah. Not with a single. I want to say that.
Justin, that question is not fair. You cannot get of course I can get a Berry curvature from single band, but you cannot get Berry curvature from single orbital.
Yeah, exactly.
Basis, that's the basis, that's the band. It's different. Yeah.
Thank you very much. Very good. I love this. Helping each other out. Very good. Happy?
So now what is the answer then? I mean, now this quantum metric, it seems that even if we need a multi-band physics. So
It's projection onto the single band.
Multi-orbital.
May not be multi. Right. Yeah, that's right. It's multi-orbital physics. I think you would agree.
So are you the Fermi surface can be of energy?
Yeah. If it's if it's complicated shape, then your task is more difficult. If it's simple shape, it's great, happy. And so the thing I want to convince you of is that this actually gives you non-reciprocity, right? So if we so it's sensitive to the direction of the wave because it's d by dr here. So the q of that wave is going to change this direction of this velocity. So if we do this, what we'll find actually is the quantum metric topology provides an intrinsic non-reciprocity to this plasmonic wave. So if I think of some density homogeneous, some kind of plane wave in homogeneity that travels to traveling wave of density, you find actually that the forward moving, the leftward moving, and say a bulk system are differentiated because of the quantum metric. Right?
So basically, to derive the above equation, you do the commutator coordinate with Hamiltonian. In the Hamiltonian have the new term, the dipole term come from the electric field, right?
Yeah. So in principle, you would do that. Yes. In practice, you would do what they call the wave packet analysis, and it does get quite hairy quite quickly. So the two references I would refer to, there's a Taylor Hughes and Lapa, Hughes and Lapa paper in PRP. There's another PRL by Xiao that sort of has it there as well. But there's some subtleties in the derivation which are actually quite hairy.
I think that's clear.
And I could it might seem straightforward, but
Is that project the dipole coupling to the band?
yeah, if it's simple for you, then I'm very happy. Very good. Great, super. So let's see what the conditions for this non-reciprocity. So the thing is, if I look at let's look at these various things. Let's look at terminal symmetry and inversion symmetry. It turns out that both the spectrum as well as the quantum metric, which governs the intrinsic spatial extent of the wave packets on either side, are the same on both sides. So k to minus k is the same. All right. So what happens if I just break one of either of them? It's there, right? So I have to break both of them. So if I break both of them, it turns out that both the electronic energy as well as the quantum metric can be different on k to minus k, and this is the way that you find there's a difference for your non-reciprocity. You want to have different propagation in the plus q and minus q directions.
So can I ask about the previous slide?
Yes. This one.
About the previous slide. So no, before that. Yeah. So the left-hand side, you don't have position limits, but how is that dealt in the right-hand side?
Oh, yeah. So very good. Yeah. So here I'm just saying that there is some electric protocol. I put the delta R here to bring down the IQ. Right. So I'm just using this number R here as a way of telling you a little bit about the position dependence of electric field, right? The quadruple moments, right? So if you really wanted to, what I'm actually saying is I'm saying that actually that there should be an R as well.
Oh, okay. I see.
Yeah, there should be. That's the velocity.
So it's about wave packet that is localized in that basically.
Yeah.
Right. What it just couldn't it.
Ah, very good. 1, 2, 3. Super. So actually all of this, right? I tried to kind of describe all of this as some kind of simple semi-classical kind of thing, wave packet moving around, very nice, and that's where the geometry really comes out most easily, right? But as we know, plasmons and screening, as you correctly pointed out, can be done, as our friend had pointed out this morning, can be done through quantum mechanical, right? And it's just a Linhart function, right? I just write a Linhart function. I should be able to actually get this. And actually, indeed, I do exactly the same analysis. And the key point here is that typically, for most plasmonic calculations, you just forget about this. So where did the geometry come from? It comes from this guy. It comes from the overlap factors. It cares for the wave function, right? So all of this quantum geometry stuff is basically saying that you have to care about the wave function, right? And it turns out that there's a very nice identity that allows you to expand this guy. So of course, this is the stuff that we saw from before this morning here, whereby you find the quantum metric is related to this quantum distance, right? But if you go to higher order, three wave vectors now instead, it turns out this is the quantum metric dipole. Right, and by just substituting this identity into this thing here, you find actually that the Linhart function screening, the polarization function, actually can be written in several parts. One is the normal thing, which depends on the Judo weight. So this is the thing that will give you the plasmons that we are that are square root Q plasmons that we like. I'm saying there's an additional correction And the first correction actually arises at third order in Q. There could be Q fourth as well, but this is the one which is not reciprocal, right? And there's only this thing here only arises when you break both time reversal and inversion symmetry.
I'm afraid that you neglected all the on-club process.
Yeah, I did.
Where you have evolved this non-zero GN non-reciprocal lattice vector.
Yeah, I didn't care about that because I was looking at small q's around my thermosurface. So I'm not thinking about stuff which is close to my boundaries.
It probably, it's valid for long-range Coulomb interaction, but for Hubbard interaction.
Sure. Yeah, but the conventional plasmons, that we try to look at are
okay.
Yeah.
Sorry, so if you look at the poles of this dielectric function, from zeros of the dielectric function, then it will give you the plasmonic dispersion.
That's right.
Right, and then can you distinguish this basically quadrupole contribution in the plasmonic spectra itself?
Yes, plus two minus two is different. It turns out there are two contributions to this thing. There's a classical contribution for the directional wave. There's also the complementary contribution as well. Right, and I'll go on and tell you just a little bit more about where these things come from and how you can distinguish. All right. So of course the simplest thing here is that you can distinguish by the frequency dependence. Right, and so basically this will kind of dominate the large frequencies. Right, so we came up with a simple model, the 1D model. Bipartite type, and it turns out you can draw out the quantum metric, as a function of decay and these various things, and you actually get you find that the non-reciprocity is actually dominated by the quantum metric dipole in this thing. So you can numerically find that out by just setting particular terms to zero. But it turns out there was actually a hidden symmetry in the system that if you set a particular parameter to be a particular number, it turns out that it looks actually perfectly symmetric. The energy dispersion looks perfectly symmetric, even though it breaks both P and T symmetry. There is some hidden thing, and so this means that the classical contribution vanishes identically, and then you actually find it's identically, not just approximately now, identically equal. You can ask another question: where would you expect the quantum metric dipole to dominate as well? Well, it turns out that where you find quantum geometry to dominate is where you try to suppress the kinetic energy. And lo and behold, actually people are looking at plasmons in flat bands of, say, TPG, right? And so if I look at TPG where I have these isolated bands that's very quite flat, you can ask, maybe I can suppress all the classical contributions, and maybe I can find the quantum metric contribution. And it turns out that I have to break both inversion and time reversal symmetry. And TPG does that. If you put it on HBN and you tune it to close to 3/4 spin. And 3/4 spinning though is a quantized non-reciprocal, right? So it's insulated. But if you dope it just a little bit, it turns out there's still some kind of Hall effect there. It's still hysteretic. So it's still magnetic, still breaks inversion symmetry, still breaks time reversal symmetry. And if we look at that, we can directly calculate the plasmons in such a system. So we did that. We found actually that there was a large non-reciprocity between forward and back. This is calculation here. And just to kind of bring home the point that it's quantum versus classical, we can just set arbitrarily in our calculation the wave function overlap to be just unity. All right. So if we did that, we find actually that not only the speculations are different, but also they're reciprocal. All right. And so this only keeps the classical terms. This keeps all terms. Right. And this shows basically that your quantum effects are important.
So what's the color here? What is the color bar here?
Oh, sorry. So what I tried to draw was basically the zeros of the dielectric function. So the zeros of the dielectric function. Sorry, let's do this. So the zeros of the dielectric function here. If I get a dielectric function here, if I set it to 0, I get a plasmon pole, right? So those plasmons are zeros of the dielectric function. Of course, there's always some kind of lifetime broadening of your system. So typically what people like to do is they try to put some lifetime broadening inside the system. And then they say they put the imaginary part of the dielectric function, which is what they call the loss function, right? So here I just plotted the imaginary part of the inverse dielectric constant. And so basically these large green, yellow things like expressions. The rest, are not touches.
So basically, the quantum effect makes the plasmon become more like stable, right?
No, it makes it non-reciprocal. Different between plus.
No, but the color, if the color bar is imaginary part of the color bar.
Oh yeah, I would not put too much weight onto this factor of 2 here. I don't think you should worry too much about that factor of 2. Yeah. The key point is it's non-reciprocal. That's the qualitative thing. So I'm interested in qualitative effects.
Is the answer to symmetry in this case? Or
No,
symmetry?
it's not.
So even for classical, you see some small symmetry.
Yeah, there's a small, you can see there's a small asymmetry. But you see it's quite large here. That's good. So it really is.
So here the particle whole continuum is outside it, like it's, or you are only floating.
Yeah, so it's all there, right? So if it enters the particle continuum, then it starts to get fuzzy.
Yes, you are only plotting the.
I'm starting the full loss function, right? So if I plot the full loss function and it's not fuzzy already, then I know that it's a donkey plasmon. Good. Great. So I think I was a little ambitious. I was going to tell you a little bit about nonlinear response. And I really wanted to tell you about the thing that we're most excited about right now. So I'm going to skip. I was going to tell you a bit about Kramers degeneracies and how quantum geometry can affect nonlinear response, but in a Kramers degenerate system. Slightly different what I talked about yesterday with you, but it's related, not exactly the same. Let me just quickly give you the punchline of this part without giving you any explanation. If you're interested, we'll talk about it afterwards. But the thing here was I was trying to look at these nonlinear things, and I was trying to tell you that there were 2 principal ways of getting nonlinearities from quantum geometry that people know. One's called the Berry-Cauchy dipole, one that gives you things like the nonlinear Hall effect. Now there is something called skew scattering, intrinsic nonlinear responses, and there's lots of interest right now in systems with PT symmetry, which have Kramers degeneracies like NBT, for instance. And one can ask the question, will you have skew scattering or BCD kind of stuff inside these materials with PT symmetry? It turns out you won't actually. They PT kind of zeros out the Berry curvature, and also kills the skew scattering. But it turns out that if you combine both Berry curvature and skew scattering together, you get intrinsic extrinsic effect. You can actually get a non-vanishing thing, and this is the subject of this part of the talk. So basically, if you use the fact there's a Kramers degeneracy, if you really use the fact there's a degeneracy, find actually there is a kind of an intrinsic extrinsic effect. We call this a anomalous skew scattering nonlinear Hall effect, and it plays a key role in nonlinear response. So that's the upshot of this. So basically that was just this part here. So I was just trying to explain to you that Kramers degeneracy, even though you might think it's kind of benign and stuff, you might be able to just add the effects of 2 copies up quite simply. It turns out you can't. It turns out that you have to think more carefully about it. And you can do this for not just simple intrinsic things. You can mix and match the extrinsic and intrinsic contribution. So that's one thing. I want to tell you about this last thing, which I really wanted to get to. Not really quantum geometrical, but it cares about wave functions as well on different layers. And this is the thing that we're most excited about right now, where you shine some light onto a material and we try to make it into a ferro-electric. All right, so the kind of idea is that there's a lot of interest right now in the 2D materials layer, 2D materials community of trying to create these synthetic ferroic phases. And so I start with materials which are not, if I look at, for instance, hexagonal boron nitride by itself, it's actually not ferroelectric. But if you stack it in a particular order, it turns out it becomes ferroelectric. If I take rhombohedral graphene, in this case, your pentalayer graphene, I would not expect it's a ferromagnet. I don't think it's a ferroelectric either. Turns out actually it's a multiferroic. And here you can see that the whole conductivity is manipulated by an electric field. And it's hysteretic. And so
Electric along the Z direction or in plane?
This is in the Z direction.
Okay.
And so you see, I can go from here, go up to here, get this butterfly. right? So it's kind of weird, right? And so we were also interested in this, but we want to make a different claim. We want to say, okay, fine, let's take multilayer graphene, right? And in multilayer graphene, if we apply a D field, which is a perpendicular to the outer plane, it gaps out this multilayer graphene into an insulator. So I put out my G there. Yeah. All right. And in this system, we know we can apply some displacement field, and this kind of polarizes my bands. So it polarizes my bands and also polarizes my layers. And so, I should get some kind of electric polarization out of this. And so, I know that D equals to E plus P from this standard kind of dielectric formula. And so what will happen is, my P will screen my D and my electric flow becomes small. My claim that I'm going to make is that when I shine some light on this, I create some kind of, imbalance energy electrons in my conduction bands, my valence bands here. I can change this relationship. So initially it was, the same sign, D and P are the same sign. I can actually change this so much so that D and P have the opposite sign. I call this anti-screen. Right, and we can do this by shining light. All right, so that's my claim, and I will try to convince you of it. Any questions about the claim? If I give more light, turns out it can even be more. And it turns out that even at displacement equals to 0, I can get finite layer polarized states. So this becomes a light-induced ferro-electric, right? From a system which was not a ferro-electric.
You care about the polarization of the light?
No.
No.
What about the intensity of the light?
Yeah, it has to be a reasonable intensity. We'll talk about the specific numbers in a second.
What happens if you turn off the light again?
Then it goes away.
It goes back to zero.
Yes, the thing is, the electrons will recombine, right? Then it goes back to origin. Okay.
So what's the frequency of the light you request?
Around, just to make it to that transition.
Typically at what type of energy?
Let's say around 50 MeV or
50 MeV.
So this is around 10
Terahertz?
terahertz.
Yeah.
10, 11 terahertz. 50 divided by 4 is something. 12.5. 12.5. 12.1 actually, that's the question. 100.1. Okay, good. Happy? Good. So it really comes down to the band structure in these layered materials actually depending a lot on applied electric. So typically when I look at, say, silicon, I look at silicon. If I apply an electric field, right, the band structure doesn't change a lot. Nothing really, maybe there might be small changes and some stark effect maybe, but it's going to be about the same, right? But in layered materials, it makes a key difference, right? So I can go, for instance, from a gapless semiconductor, open up a gap and make it into a semiconductor, right? And so it makes it, and the key thing here is the gap is locked to the layer distribution, right? Where my electrons like to be on, right? And so we're going to use this fact to try to create this outer equilibrium system. And so you get a lot of various interesting things with layer polarization so people have used deep field induced layer polarized states for various things, including to control quantum geometry, construct topological states, control something like the value selective Hall effect, and so on and so forth. And it also controls phases of matter as well. So people recently have found that when I apply some D field, and I want to say Romanese graphene or even Bernal stack graphene, like micrometry somewhere around here, I can access large bandwidth singularities, and you get all these fractional metal states. You get basically, like a anomalous Hall effect in a quarter metallic state. You can get half metallic states as well, and so you can use your D fields to basically do a lot of very interesting things. Okay, so this also activates second order nonlinearities. The key thing I'm trying to do here is that when I apply light onto the system, it actually allows me to change layer polarization as well, right? And we can see this quite easily. So that's the key idea I'm trying to push is an idea of the symmetry gradient, not from the typical broken symmetry phases of matter, this Landau paradigm whereby see I lower my temperature or something, I basically go into this kind of potential minima. I'm saying actually I really care about the dynamical phase of matter, whereby I look at broken symmetries dynamically, right? In the dynamics of my of the system, right? So not in the stacks. And so this is what I claim. So let's get down to the how it comes about. So if I have no d field applied, let's say a layered system like this, right? Then I get a dispersion like that, right? So it's it's a gapless segment, right? If I apply a d field, basically what happens is I open up a gap, and that gap basically depends on the amount of potential that's sustained across that layer. And what really happens is that close to the band bottoms here, we find that the top layer now becomes mainly in the conduction band. The valence band is mainly in the bottom band around this part, right? And so I can use my d field to basically change my potential energy landscape of the system. So one way of thinking about it is that when I have d field equals to 0, I equally populate both top and bottom layers, right? But now when I apply a d field in either upwards or downwards direction, I will prefer one of the layers. And that's because there's some energy cost, there's some electrostatic energy that will prefer one or the other. It's quite simple. All right, and the screening actually arises from this polarization using the system here. So let's care about the very simple case, right? So let's say I'm at 0 d field case now, and there's no electric field across my system. I apply some d field, all right? I will actually now, layer polarize my system. I have more electrons now in my bottom layer, and this gives me a polarization upwards here. And actually, this means that my electric field should be smaller. So E equal to D minus P. So if D and P are in the same direction, right, E becomes smaller, reduced. So have people seen this? Yes, they have. So it turns out that back in the day, when they first found that you could control band gaps in bilayer graphene, so this is Feng Wang and Yuanbo Jiang paper in 2010. They applied some d fields. They found that the band gaps they got was actually a lot lower than what they expected. They expected from an unscreened kind of thing, quite a large band gap, right, when they applied some d field. But it turns out the experiment was much smaller, and could be explained by some kind of self-consistent screening from this polarization stuff. Okay, so that's nice. That's equilibrium. We all understand this. It kind of goes with our expectations.
Yes. Question: is the transition is there any selection rule you need to consider?
No, but we actually did consider the selection rules, but it wasn't really important.
I see.
The selection rules from certainly polarized light, but we didn't have to use certainly polarized light. We just used really polarized light. So it's not so for the speed to work. Yeah, but it just goes up. We just care about optical transitions. So we didn't want to select a particular value or not, right? So maybe you're thinking about this thing here. If I use certainly polarized light, I get this value selected pole. Right? Yeah, sure, that's true. But we didn't need it for our scheme. So we use linearly polarized light, excite both K and K prime. That's fine, that's okay. Thanks. Yeah, so we'll get to all of this. So the 10 minutes that we have left, I will try to convince you that we'll get these kind of interesting phases.
The only charge is transport or 2 layer is rejected. Some possibilities you are charged of 1 layer to the other is possible. My question is 2 layer is here. The real system is each layer has make a dipole or some charge move to the other side.
Yeah, it's an interlayer charge transfer. Yeah,
it is possible. Or
it is possible, right? So if I shine some light, I can kick I'm providing energy, right? It's not zero energy, right? Providing energy, I can kick my electron from the bottom layer to the top layer. That's what happens whenever I do optical transition in this specific.
In your result, what each kind of charge transfer is important?
Yeah, we'll get to it in a second. So I think I made the claim, and then you're trying to understand the claim. I haven't actually explained the claim at all. So all these questions come up, but we'll get to it. Don't worry too much. But if I didn't answer your question, you can hammer me afterwards and ask me questions, right? Yeah. So we'll have this. So I'm just trying to explain to you that we're really that the polarization charges were very important. So you actually get good statistical agreement with your backends, right? Right. But what happens when you photoexcite? Precisely what you just said. Basically, I can push one electron from my bottom to the top. That's exactly, but it costs energy, but the light can provide some energy. So it's exactly what happens. So it provides some energy and self-consistently reorganizes your potential well, because your electric field now has changed because it's been screened. It's now screened less, right? So as you can see, so if I go back here, my polarization used to be quite large. The electric field that I had, the total electric field was actually quite small. But now when electric field basically will tell you that difference between the potential magnets. But now if I push some electrons up from the bottom to the top, I will change your effect. He becomes small. And actually my electric field now becomes a bit larger, right? And so in doing so here, I can change my polarizations out of equality. I can do it so much that my electric field, if my P now can change signs. I call this anti-screen. And lo and behold, now your electric field now is larger than your applied D. It's very weird, right? In equilibrium, this is not allowed. And so I call this anti-screen. The total electric field now is enhanced, not reduced by polarization. Yes.
So so I think it can both reduce or enhance the polarization.
Depending on the photoexcitation.
Does that depend on the density of states?
Yeah, you put it all in your calculation when you do it. But yes, that's just the amount of charges that you have pushed from your bottom layer to your top. So this is the weird anti-screen regime that you can have. And the reason why it works is because we take into consideration the wave function. It turns out that when we apply a D field in this layered system, most of the electrons close to the band bottom are really very localized on the top layer or the bottom layer, or to my conduction on the top layer, right? To my top layer. And my valence band is if it's close to the band edge, it's localized to my bottom. If I go far away from the band bottom, they're not particularly well localized, right? And so the electrons here control the polarization of the system. So when I make a photoexcitation and the electrons now go to the band bottoms, the band extrema, then those electrons, those photoexcited carriers there actually control the screening properties of the system. And that's the key point here. That's how it's connected with geometry, right? Because it cares about where the wave functions are, right? And so we can calculate all these kind of things, and we can start, for instance, here without any photoexcitation, my E's and P's are in the same direction. And as now we apply some light, we basically change the polarization as a function of electric field. And you can see that you can make it highly nonlinear, and you can make it even more nonlinear. So you can find here that now my polarization here is negative, even though my electric field, right? And so light induces this anti-line polarization, and allows you basically to get this anti-screening regime. So this is kind of weird already. This result by itself, I think, is already very unusual. But we go further. So let's first kind of focus on this linear regime as a function of E field applied perpendicular E field. All right, and we can kind of characterize this by these, by non-equilibrium susceptibility. And basically, you'll find that we go from some positive non-susceptibility to become something negative, right? And you'll get basically a regime here which is between 0 and -1, right? And then you also get a regime here which is less than -1, and they have a particular significance. So it turns out that I won't go through all of this consistency stuff because we have 5 minutes left. But the upshot of this is that in this part here is screening. I get reduced electric fields. This part here I get enhanced electric fields, and this part here I get reversed electric fields. This overscreening regime. And this regime here, which has enhanced electric fields, is actually not allowed by equilibrium thermodynamics. So if you search the literature, it turns out that in the 80s, there were actually constraints on screening in equilibrium. They found that actually the dielectric constant could only be could be only smaller than 0 or greater than 1. It couldn't be between 0 and 1. And so that means susceptibility can't between 0 and -1. And so as a result, actually, this violates what you expect in equilibrium. Of course, we're okay because we're out of equilibrium. We find energies of the system to violate this criteria. So we can only achieve this non-equilibrium relative conductivity only out of equilibrium, and we provided energy for this this case here. There's also another regime where you get overscreening, as I told you. And so here, it turns out that the electric field or the field here becomes the opposite in sign to the prime that I have. And so this is the overscreening regime. And typically overscreening comes from correlations. And here we're achieving it just without implementation. All right. And so actually it turns out that we just focus just on the linear part. If we go to the full nonlinear part here, I only focused on this part here. I kind of wiped it out. The rest, it turns out there are actually additional solutions to this self-consistent equation that we have here. And these actually define some kind of ferro-electric phase, right? And so it turns out if I draw a full phase diagram and apply some kind of various intensity in the fields, you asked about intensities. So these are 5 kilowatts per second squared. We did a kind of realistic simulation with this. It's 40 kilowatts per second squared and 25 kilowatts per second squared. We find basically that there is a kind of a non-zero polarization that gets reduced even when deviating to zero. And so these are kind of way within the regime of powers that can be applied in experiments.
Yeah, how to compare with the gap in your basically system, like displacement scale induces a gap, and how to compare this with the gap in the system?
Yeah, so this is the gap, vertical potential energy drop. That's the layer potential across both layers. That gives you the gap. Right. So the gaps that we get around 10 and 80.
So how much graphene bilayering is important? I mean, if suppose that you have a two bands, one electron, hole type, one electron type, and they are located on different, let's say, layers. Then you put light and then get some transition in some way to different bands. Then again, it seems that some polarization happen because electron is pumping maybe to other bands. Same happen, yeah. I mean, I want.
Exactly what we're calculating.
No, I mean, the very curvature is important here or not?
No. So this was screening, right? So this cared about the polarization. So I'm really sorry because I thought because you might think this is related to quantum geometry.
Yeah.
It is sort of related, but not really. Right, so our friend would say that I could have calculated this just with quantum mechanics. That's true. It's true. The main thing that I'm trying to show you here is that to be able to understood where the electrons are, I needed to care about the wave functions. And I'm saying quantum geometry and wave functions are very, very important. So here, what have I calculated? I've calculated the expectation value of my polarization operator. Right. So when I think about connections, stuff, I think about basically expectation value of position operator.
Polarization is just which layer is give mostly contribution to that.
So this is a layer polarization operator. There's a little different from just a simple position operator. We can talk about the differences afterwards. In plane, it's the same. Out of plane is different. So out of plane breaks the symmetry. In plane doesn't.
Do you think about the
Phonon effects, yeah. So I've gone through all. Yeah. So quite quickly, to be able to get these curves, these were fully self-consistent curves, which took care of, say, the temperature of the electrons. The temperature of electrons are quite important, and so the electron-phonon interaction is very important there to cool the electronic gas, the photoexcited electronic gas. So they took into account the phonon effects there as well, and there's also a recombination effect as well. So it turns out that recombination is not well known theoretically in these gap systems, but actually people have measured it. So we just took the measurement and said, okay, fine, we don't know how to calculate it, but the measurement is there. Let's just take the measurement, put it in, that's it. Precisely, yes.
For example, one has value multiple.
That's right. So the key point was when we get into the overscreening regime, we allow for multi-stability to happen. Right? So it turns out that you get multiple self-consistent solutions even at the same time. And that's the key point with this light-induced ferroelectricity. I'm trying to create multi-stability in the system without actually having a truly truly interactive system. Right? It's just done in a meaningful way. Right, and so I think that the key thing that I really wanted to explain, I was going to explain these two cases here, was that that it's a slightly different kind of paradigm of kind of symmetry breaking. Typically, we think of conventional screening, is at equilibrium, and conventional ferro-electricity, arises when I bring my temperature down, I break the symmetry. Here, this non-equilibrium anti-screening is not equilibrium. I'm really just pumping the electrons, and they sit at particular layers determined by the wave functions of their materials, right? And actually, the symmetry breaking arises from a multi-stability, not from some kind of Landau kind of paradigm, but from some multi-stability driven by some kind of light, right? So that it comes from nonlinearity and polarization driven by light, right? So I understand that it was not super clear.
Still that figure.
Yes.
Yes, this figure. Actually, only difference, if we only consider the slope of this line, only around the 0 point, around this part, there is multiple line. Beyond that region, this red and the yellow line have very similar slope.
Yes, that's right. So basically, there's only a series of D fields whereby you actually get this multi-stability. That's right. So I realized that I wasn't explaining it very well. So the key idea here is that when I pump my electrons from the inside, right? I change. Right? But if I have larger and larger D fields here, then eventually, this wave function overlap. Sorry, this wave function expectation value will change as a function of D field. So it becomes more spread out, more and more spread out. It becomes more and more spread out. Then basically, then we need more and more electrons now to control the polarization. But then if I apply large D field, I keep the same number of electrons that I photoexcited, then I can't actually flip the photo. That's why it goes back up again. And so that's why you have only a specific range in which you can really control the polarization with this outer plane. Sorry, this outer cooling excitation. Right, so hopefully that's good. Great.
That kind of thing is it possible to understanding in the electric state to the ferro-electric state?
Para to para?
Para-electric to ferro-electric.
To the ferro-electric state. So I hesitate to basically say that it's actually a true ferro-electric state. It looks like a ferro-electric state, but it's not quite. Thing is, if I started at this point here, it doesn't spontaneously, and I shine some light, it does not spontaneously jump to this. I actually need to do some hysteresis. I need to apply some D field here, get onto this solution, and come back here.
But the kind of shape is typical behavior of the water parameter in first phase.
But it's not.
Yeah. So it is like a phase transition. But because we did it in this non-equilibrium kind of way, it's quite difficult to understand it in the usual sense, right? So we don't have a free energy diagram for this. We only have a dynamical, bistability, multi-stability for this system. So hopefully that works.
But I guess you have like non-equilibrium, right?
Yes, non-equilibrium.
So it's not the same like state.
It's not exactly. It's not the same, and we even find regimes which are explicitly forbidden at equilibrium, but not forbidden out of equilibrium, which is this anti-equilibrium where my electricity. Right. So I leave you with this. Thank you very much for your time. I just wanted to say that we have some openings in our group. So if you're interested, if you know people who are interested, please tell them. So thanks very much. Lots of questions, please.
At the beginning of your talk, when you talk about that semi-classical equation, and after that, when you introduce can you go to this?
Sorry, yes, yeah, just which, because a lot of slides I'm going to use.
Yeah, at the beginning. But
yeah, so maybe
after
you can tell me which.
I couldn't realize the relation between, I mean,
which one?
Go down. Yeah, this one and the later on, I mean, and this non-reciprocal and this plasmonic dispersion energy.
Yeah.
how, I mean, they are related.
Sure. So I'm sorry for not truly very well. So a plasma basically is a traveling charge density,
Okay.
right? So basically, I think a plane wave of charge density, right? So a charge density is going whoop, like that, right? So if my density is changing as a function of position, I have Coulomb potential, right? Coulomb potential tells me that the density change as a function of position will therefore translate to a change in electric potential, right? I'll get now changing electric function of position, right? And therefore I get a change in electric field as a function of position as well. Some kind of wave-like way as well. So that changing this density changing here will change the electric field. That electric field will go in this, right? And that will change the current. Oh, but wait, that current now will drive a change in density, right? Because of the continuity equation. Partial T of n plus nabla dot j, j is current, is equals to 0. So if now I've changed my current, that will now feed back into the density. Oh, but changing in density changes my electric field. So I get this feedback, right? So there's a feedback. And basically then the feedback comes from this. So this allows them to, like, I'm going to I didn't at all. So plasmons can be understood as it's the same thing as looking at Maxwell's equations, right? How do I get EM waves from Maxwell's equations? I look at basically Ampere's law and Faraday's law, right? So I have these two things and they feed back with each other because of the displacement current, right? So it's the same thing here. So this basically here allows you to feed back. And the thing I did show you was basically how this electric field is coming about. This electric field is being created by the plasmon itself. Because it's a density wave that's inhomogeneous in function of position. If I had just a constant density, or no, this is not there anymore, right? Because it's a R. And then I also would not get any potential as well, right? Great.
Yeah, so if I have a non-reciprocal wave, just like your plasmon here, like left going, right going, they have for the same wave number, they have different frequency. What will be the standing wave? Do I still have a standing wave? Probably not.
Yeah, probably not. Good
Yeah,
question.
so that's a very big consequence.
Good.
Right,
So
yeah.
That's good. Thank you very much. The consequence that we were thinking about was technological, right? The consequence was to make these it's called a circulator, right? So people use these circulators for technology to do mixing and stuff. So that we were thinking of that, but we didn't think about the standing wave. So that's a good thank you very much.
Regarding the second part, so
Yeah.
sort of technical question. So when a displacement reflects the inversion symmetry, that is time versus symmetry.
With inversion symmetry, not time inversion.
So so inversion symmetry.
Only inversion.
Okay, so when you do the band like this calculation of renormalized band structure,
Yes.
you use the high frequency or the source wave, what kind of
Oh no. No, there's no. Okay, very good question. Yes. So the kind of nice thing about this calculation here is that we didn't care about Fouquet at all. Right. So the criticism typically given with Fouquet is it's a coherent phenomenon. Right. I need some coherent kind of thing. And what happens if you have scattering? I can't even deal with it. Right. We should put some bath inside and people will cry all the time and give names and stuff. Right. So we said, okay, fine. I don't want to do that. Right. Let's just embrace incoherence. And incoherence comes very easily in photoexcitation. Right. So when I now shine light from here to here, will my electrons stay up here? It won't stay up there. It will go down, right? And it's going to lose its coherence. Right. So scatter with other electrons, scatter with phonons, scatter with disorders, scatter with anything there, right? And then it's going to pull up here at this point here. And that's all we care about. We only care about the fact that we have a lot of electrons pulled up at the bottom of my band extreme, right? Or holes, right? And so it's incoherent, so it's not okay. And so then you can ask, oh, so how do I calculate the band structure of the system? Oh, okay, simple. I apply the D field here, and there's a polarization involved, right? I just put it in. That's it. So it's a completely kosher calculation, right? But of course, I think about this long time limit whereby all my electrons have now quasi-equilibrated to their band edges. Of course, there's some recombination time which we take out from experiments, right? And as a result, we miss all the coherent effects, right? But the coherent effects can be quite fragile. So that's no harm, no foul.
If the band becomes flatter, its region will become
Larger, that's right. And then you would expect more electrons to be able to control this polarization. That's even very good. And that's why actually, in the end of the day, we looked at rhombohedral trilayer graphene. When you apply some kind of displacement field, it turns out that the band bottoms and the band extreme of both the conduction waves become quite flat. So there's a large density of states there. It allows you really to control the polarization with those electrons that you put inside.
Yeah, I remember in the second part, you go very fast, talking about some nonlinear effect, some like school scattering, but a non-school scattering. Could you give some more details?
Oh, sorry. So because I really
just about the conclusion. Yeah, that would be good.
So the key point was the following, right? So the key point was that promise symmetry actually imposes very, very strong constraints onto things. So if I look at spinless fermions, for instance, right? So spinless fermions tells me the Berry curvature is compensating omega zero, nothing. And I can also ask, okay, what does PT symmetry have to say about scattering? So it turns out that there are various kinds of scattering involved. There's normal scattering, but there's something called beyond Born scattering. That's skew scattering. So
that breaks PT symmetry.
Yes, it does break symmetry, but no. But the impurities don't break PT symmetry. Process. We'll get to that. So it turns out that typically when I look at Born limit, I always would say that the transition rate from K to K prime, and this is not value. This is just momentum. Momentum P1 to P2 should be the same as P2 to P1. So you would expect this from Fermi's golden rule, right? Some simple thing. Turns out that this is not the end of the story. It turns out that for something called skew scattering, I can go to these processes that are not matrix element squared, but matrix element cubed, right? And basically you can have P to P, P1 to P2, not the same as P2 to P1, right? So these are what we call skew scattering. And people have looked at these things to look at nonlinearities. And so there's an experiment that basically showed that they dominated nonlinearities in graphene and boron, right? And they dominated over Berry curvature diagram. But you can also look at the same expressions and then ask, what happens to skew scattering in the presence of PT symmetry. So in a spinless model, you actually find that the skew scattering actually goes back to actually preserving P1 to P2 same rate as P2 to P1, right? And we kind of looked at this and it was like, oh no, that means both BCD effect vanishes, skew scattering also vanishes. So if I did this for just a spinless system, I would conclude that skew scattering does not play any role in the nonlinear Hall effect of a PT symmetric system. I would also conclude that BCD has no effect in the nonlinear Hall effect of a PT symmetric system. All right. So
what is BCD?
Sorry, Berry curvature diagram. Sorry, Berry curvature diagram. I'm really sorry. I used a lot of acronyms. Right. So that's that thing, right? So as you know, these two effects are kind of the main effects that people are talking about. But what happens now if I consider spin-full fermions? And the point here is that if we consider spin-full fermions, there's something called half-integer spin. And half-integer spin tells you that actually the Berry curvature actually is compensated, but it's compensated between spins, right? And same thing for skew scattering. Skew scattering is also compensated, but it's compensated between spins. So this is odd under PT. Berry curvature is odd under PT. That's why the PT symmetric system should vanish. This is also odd under PT. What happens if I combine these two things? Odd is equals to even. That was our potential idea. So people typically don't like to mix intrinsic, extrinsic. We mixed it and we found a non-zero effect from a vanishing effect. So this is part of something that we're really trying to push right now called Kramers nonlinearities. Basically nonlinearities that would naively vanish in spinless systems, but will be there when I consider spin-full systems of half-integer spin.
How we can measure it?
By
Okay, the system that I explained to you also is some kind of this one, but up and down are coupled.
yeah. So in the inverse system, I think you really cared about P and T preserve. So you have it here. I wait for P and T.
Okay.
And but I look at this. So it turns out that there are these materials which break PT symmetry from MBT. I don't know if I have it here. I don't have it here. And then you can just kind of measure things like circular photocurrent in the intraband limit, or you can also measure just the non-uniform thing. So this is a well-known way of doing this. Or copper manganese phosphate is antiferromagnets. I know I'm severely over time, so if you want to tell me to run away, I can do it. And also, I'm sorry for being so quick about everything. So if you have any questions, I'm very more than happy to answer them.
Okay, so if you do not have urgent questions, let's finish first.